Welcome all. We will see today the function of microwave test bench for the wavelength and frequency measurement. So this is a complete microwave test bench and it is based on the klystron tube. This one is a klystron tube and this particular component or part of the waveguide is known as a klystron tube mount. The second component is the isolator, and you can identify the isolator as a two-port component, and one arrow depending on the direction of propagation will be placed, and then it is followed by an attenuator. We can able to modify the amount of signal which is propagating through this to be attenuated, or attenuation may be reduced by rotating this micrometer, which will be able to control the position of the resistance resistive or the absorber 1A inside the waveguide. The fourth component is the frequency meter. We can able to read the frequency meter in this range, and if you have a closer look at this, you can see there is a printing, or the values of the frequencies are written starting from the 8.4 gigahertz to the 12.4 gigahertz. So as the size reduces, the corresponding wavelength is also reducing, which increase the value of frequency. So less size reduction will be able to give you high frequency. So this works on the absorption of the top propagating frequency signal. The frequency which is propagating through the microwave source, here is a klystron tube. This matches with the klystron generating frequency, or this cavity generating frequency. Then that particular frequency will be absorbed, and we will have no signal or less amount of signal off to the frequency meter. So this is an absorption type of cavity resonator. The next component is the slot line section, and this is it is having a slot on the top of the waveguide, so that's why it's having a name slot line section. We can able to change the position of this probe. A probe is used to detect the electric field which is forming inside the rectangular waveguide, and we can change the position of this probe, and you can able to see the corresponding change on a CRO. So it is able to show you the corresponding electrical strength at that particular location of the probe. So this complete section is known as a probe, and a diode is placed, which is just like acting like a rectifier. So any micro signal power is rectifying to the low frequency signal, and then it is directed by the visualometer or with the help of a CRO when can able to detect. We also connected one more component that is known as a detector, and you can see a diode is placed, a crystal detector diode is placed in between this, and power from the crystal diode can be taken to the two meter. One is again the visualometer and the CRO. The next component, I just place a short plate which will able to show us a high reflection, and then it is followed by a mesh termination. So although if you are placing a short termination, there is no requirement of a mesh termination, just for understanding that any termination line which is able to propagate a signal also is required to be terminated at this end. So just this mesh termination is placed. So this is an overview of a klystron based microwave test bench. The major equipment here is a klystron power supply, and you can see here some number is displaying. So the proper setting of a meter, like right now it is showing the position at the V, so it is showing the 267 or 268 volt, which is applied to the CRO, which is applied to the klystron tube, and the same meter can also show us the current, what is current is flowing or not. So this also confirm that whether the klystron is working or not. If no current is flowing, that means klystron is not working. This is also showing a Rippler voltage. Only for representation the REP is written, and Rippler voltage is also always a negative bias voltage, so always a negative sign is coming. So we can able to change this voltage by changing this control knob, which is designated as a beam here, and we can able to, you can see the voltage is changing, and similarly we can change the Rippler by changing this Rippler knob. So by having a proper control of the beam value and the Rippler voltage, we can able to generate the square wave required for the propagation in terms of a microwave signal. We can able to modulate this high frequency signal either using a continuous wave, amplitude modulated wave, frequency modulated wave, or any external signal can be given. For external signal, this is the we can apply the external signal using this BNC cable for the modulation. Okay, so you can see here for the amplitude modulation, these two knobs are used. One is controlling the amplitude frequency, one is controlling the amplitude of the frequency. The other two knobs are for the frequency modulation, again controlling the frequency, modulating frequency, and the amplitude of the frequency modulating signal. So these two knobs are present, and you can see here that all the klystron tube as well as the modulated signals are going by a number of cables, which is combined as a single cable. You can see here, and they are feeding to the klystron tube. So the first question should be come in your mind: why the modulated signal is required in the klystron tube bench? That we will see later on. And then we are having a CRO. I am not going to explain about the CRO, but right now I just tuned a CRO so that we can able to see the square wave. This square wave is just depicting depiction of the modulated signal, and since we have modulated using a square wave modulation, that's why a square wave is shown on the display of a CRO. The next component is the VSLOR meter, and as we can see here, we can able to control the needle position by controlling the value of a gain. If you wanted to change a small position requirement for the needle, you can use the fine knob. Okay, so this explanation of the expand, normal, and -5 dB is already given to you in the theory class. And a range selection can be made 0, 10, 20, 30, 40, 50, 60. So although they have not taken the minus sign, but you must understand that the this is -20, this is -30, -40. The aim of this range selection is to have the ring, this needle, to be in the in the range of meter. Now focus again on this important meter. This meter, as we discussed, this is showing the VSLOR value, then expanded SLOR value, dB value, and the expanded dB value. So if the knob, this particular knob, if this particular knob is set at expanded position, one can read the reading for the SLOR in the expanded SLOR and for the relative power in expanded dB. So these scales are given here for reading the SLOR directly or reading the relative power coming out from the microwave test bench. Now we are going to read the frequency meter. Okay, so what is the first condition? That we will assume that some frequency signal is coming from the klystron tube. For that we have to read, and the reading can be made directly using this cavity resonator or the frequency meter. The theory of the concept is same, that if any resonant frequency which is generated by the cavity resonator is matches with the operating frequency, it will be absorbed by the signal. It will be absorbed by this cavity resonator, and we will have no signal or less signal on this side. So currently, I have connected the detector with a CRO, and the CRO is currently showing us a corresponding value of power or amplitude on its display. Okay, so let's say this is some position, some amount of power. We only need to require a relative measurement. We do not require the absolute measurement of power or the voltage. So now focus here, and at the same time you must focus on the display also. Okay, so I'm rotating this one. As I'm rotating, the corresponding position of the plate which is inside this cavity resonator is moving down, and we will also at the same time focus on the CRO display. So that will be shown us the reduction of the power in terms of the reduced voltage per division. So since we are newcomer, we will move this, or we will rotate this frequency meter very slowly. You can see the reduction of the amplitude on the CRO display started. I have to stop my hand where this reduction will not reduce further. So this is a position. This is the position. You can compare to the previous reading. This is a voltage division value is reduced. Now I will read the value from here. So we will read the value which is corresponding to this vertical line, and the reading must be lying between two horizontal red mark. Okay, so this value is right now 10 point 10.05015, and this side we are having a 10.1. So this value is less than 10.15 gigahertz, and let's say I'm moving from lower value to higher value. So this is 10.1, this is 10.11, this is 10.12, and this must be 10.13, and then it is one more division. So this is 10.135. So I will note down my frequency, which is measured as 10.135 gigahertz from frequency meter. Now we know that one formula lambda naught divided by C by F, and this is equal to 10 to the power 8. Let me take centimeter, 10 to the power 10 centimeter per second. It's 10.135 into 10 to the power 9. Okay, so this gives me a small 30 divided by 10 power 135 centimeter. So this value is coming as if you take this ratio, the value is coming as 30 divided by 10.135. So this is 2.96 centimeter. So this is the value of lambda naught. Okay, so we have done the frequency measurement, direct frequency measurement, and we can able to obtain a free space wavelength. So this quantity we are designating as for frequency wavelength in centimeter. So this is 2.96 values coming at 10.135 gigahertz frequency, and we know this formula, the relationship between the lambda g, that is the guide wavelength, and the lambda c, which is equal to 2a for the propagation for the dominant mode for a rectangular waveguide is 2a. So lambda c we calculate 2 into 2 to the power 286 centimeter, and this is coming as 4.572. So if you go by measurement for this is the A dimension, broad dimension of rectangular inner waveguide. So if you go by measurement, the value may be come about 2.2 something, but we will take a standard value 2.286 centimeter, and from there we have calculated a cutoff wavelength. So this is cutoff wavelength. We can use the formula 1 by lambda naught square divided by 1 by lambda g square plus 1 divided by lambda c square to obtain the value of lambda g. Okay, so this is a formula one can able to obtain the value of lambda g by putting the value of lambda naught and lambda c. So you have already seen that how we obtain the value of lambda naught and lambda c. You can calculate this value. Another method of finding the lambda g, I am telling you, with the help of using our Sutherland section. So we have discussed this part, that our Sutherland section we can able to move, and depending on, since we have connected a short, there will be the multiple positions for the maximum, V maximum and the V minimum. So by formula also we obtain the idea that we can obtain the value of lambda g by taking the difference of V maxima position and V minima position. We can also able to take the lambda g, since lambda g is like that for a standing wave. So this is the position for the V minima and this is the position for the V minima. At the same time we are having the V maxima and V maxima here. So from V maxima to V maxima, the complete length is given by lambda g. This is lambda g by 2, whereas the relationship between the location difference between the V maximum and V minimum is lambda g by 4. So we can obtain the value of lambda g by taking the two position or the difference of the V maxima position 1 minus V maxima position 2, or we can take using the value of V maxima, let's say position 1 and let's say position 1 for the V minima. So we can use either this formula in terms of the two maxima position or in terms of a one maxima and the one minima position. So best method is that either you go for this kind of formula, because getting always the same value or the difference between the location of the V maxima and V minima may be not same. So I prefer to use this formula. And as you can see here, okay, so see here I am changing, and at the same time focus on the CRO also, that when I am changing, it is changing its total amplitude and the value of V maxima and V minima. So like this is the position of the V minima where the amplitude is less, and this is the position of the V maxima where the amplitude is large. So if I rotate in a complete scale, let's say starting from here, and then when I am rotating, you can see multiple positions of the V maxima and V minima we can obtain. So we can use the two formulas which I already discussed on the page to find out the value of V maxima and the V minima positions. Okay, let's say I'm starting from one end. Okay, I'm going to do the right measurement. Okay, just I'm putting my proper position on a CRO. So I'm starting and moving in one direction. The probe is moving in one direction. So let's say this is a position of the V minima. Although it is not readable because this is very old, but you can see there is a vernier scale is placed, and let's say this reading is. So we will put the probe position to the minima. So we can check the position of the V minima from here. And I just noted down the value of V minima. First V minima is coming at 8.80 plus 0.03. That means 8.83 position. Unit of this scale is in centimeters, so centimeter I kept. When I'm moving further in the same direction, I got the position of second minima. So that can be checked on the CRO display. And this position I will treat using the main scale and the vernier scale. This reading is done 10.9 plus 0.01 on a vernier scale, and this value is 10.91 centimeter. Further, I will moving the probe in the same direction. I got the third V minima position. We can cross check from the CRO display, and the reading of the V minimum can be read from this is scale. This is coming at 12.90 plus 0.06. So this is 12.96 centimeter. Further I am moving, since still there is a scope of getting the V minima. So V minima I placed over here, which I am reading, which I read from the scale, 15.0 plus 0.03. This is 15.03. Okay, so I can take the difference between these two values, difference between these two values. So the lambda G to 2 into V minima, 1, let's say V minima, 2 positions. I have calculated the 3 values, so I can take the 3 values. First value is like 2.08 plus this 2.08 is coming as a difference of 8.83 minus 10.91. Then I am taking the second difference, 10.91 and 12.96. This value is coming 12.96 minus 10.91. This is 2.05 plus, since I am going to take the average of the 3 values, 15.03 minus 12.96. So this is 2.07. I took the 3 positions, so I will taking the average of 3 numbers. This is actually coming 2.08 plus 2.05 plus 2.07, 6.2 overall, divided by 3. This is 2.06. So 2 into 2.066, or it's coming infinitely. So lambda G is equal to 2 4.13 centimeter. So this is the value of lambda G which I obtained using the Jordan section. The same kind of a V maxima and V minima positions you can see. I am just changing the probe position, and you can see the deflection moment. So this is going toward minima. Now the scale is moving toward maxima. Okay, to have a better understanding, you can use these knobs. You can use these knobs to, you see the needle. I'm trying to keep the needle on the V maxima position, so we can easily read the V maxima. Okay, now you can focus on here. Okay, now I'm changing the probe position. This is maxima position. It is going towards minima. So the needle is moving towards left corner. And then after moving from the minima position, it is moving back to the maximum position. So we can also find out the location of a V maxima and V minima using the VSLOR meter. So this is for the day to day. We will see the VSLOR measurement in next class. You can also see here. Okay, for VSLOR measurement, I will just do the quick measurement. I'm trying to keep the needle at a V maximum position, and adjust the needle to VSLOR equal to 1. Okay, so normally we are defining the VSLOR as a V maximum or the V minima. So let's say on the top scale we are reading, and when I am moving towards the minimum position, the needle will move towards the left side. Okay, so it is moving towards the left side, and since it has crossed the first scale, still when I am moving the same direction, so I will change the knob since I created a short. So this is whatever the reading of VSLOR I will read, that will be more than 10 now, since I change the range switch by 10 dB. I am moving in the same direction. Now you can see here, from here, it is returning back. So this is the position of the V minima from where it is returning back. So I will go back to read the V minima. So since I changed the range switch for a one time, so it's difficult to obtain the minimum position precisely when you are conducting a shot. So I think the needle has stuck, but still I believe. So it's difficult to get a minimum location, exact minimum location or minimum value while we are using a direct visual meter. So in the next class, we will see the visual measurement on a visual meter, and also we will see the high visual measurement using double minimum method. So this is for today. Okay.